Hi everyone. This is a continuation of our discussion about section 3.3 in our text, which is about ring homomorphisms. So first, a little bit of review. So if you have a couple of rings, R and S, and you have a function from R to S, that function is a homomorphism if it respects both addition and multiplication. So that is, if you take two elements A and B in R and you add them together and then apply F, that would be the same result as if you first took F of A and then F of B and then added the results in the ring S. And similarly for multiplication. So if in addition your ring homomorphism is bijective, then you have what's called a ring isomorphism. And we saw last time that if you have a ring isomorphism, that means that the two rings R and S are essentially the same ring. That is, that any difference between them is entirely superficial, and that sort of the intrinsic ring properties that they have would be shared in common. So for instance, if R and S are isomorphic rings, then if R is commutative, S would have to be commutative. If R has identity, S has identity. If R is a field, then S is a field, and so on, and so on. So, last time we spent a lot of time talking about isomorphisms, and the question today, I think, is, well, if you just back up and look at a ring homomorphism without necessarily requiring the function to be bijective, what can you say about what sort of properties does S get from R from such a thing? So we will talk about that here in just a moment. So suppose we have a ring homomorphism F from R to S. Then there are some things that must happen. First, if you apply F to the zero element in R, the output has to be the zero element in S. It can't be anything else. Second, if you apply F to the additive inverse of A, then the output must be the additive inverse of F of A. And third, if you apply F to A minus B, then you wind up with F of A minus F of B. So that is F, in addition to respecting multiplication and addition, also respects subtraction. Then if you start with a ring R that has identity, and if the function F is surjective, then you're able to conclude that the ring S must have an identity, and that you get that identity just by applying F to the identity in R. And then again, finally, if R is a ring with identity and F is surjective, meaning it's onto, then if you start with a unit in R and you apply F, you wind up with a unit in S. And in fact, the multiplicative inverse of F of U is obtained by just applying F to the multiplicative inverse of U. Now we're going to talk a little bit about the proof of theorem 3.10. We're not going to do all of it. We're just going to do a little bit. So we're going to do parts B and D. So you might recall that part B said that if you have a ring homomorphism, then the additive inverse of F of A is F of the additive inverse of A. So how do we show that? Well, if we take f of a and we add f of minus a, then because the function respects addition, then we can write that as f of a plus minus a. But a plus minus a is 0. And by part A, which we've not proved, we know that f of 0 in R is 0s. So the conclusion is that if you take f of a plus f of minus a, you get 0. And that means that f of minus a is the additive inverse of f of a in S. And in notation, that says that f of minus a is minus f of a. Okay, then moving on to part D. Here, I think in part D, we'll remember that we have a surjective ring homomorphism and that the ring R has identity. We're trying to show that S also has identity, and that you get it by just taking f of 1R. So we just start with some element in S, call it y, and because f is surjective, we know that there's some element x back in R where f of x is equal to y. So now we can just set up a chain of equalities. We know that y is f of x, but x is x times 1r. So we get that y is f of x times 1r. But remember that f preserves multiplication, so we can write f of x times 1r as f of x times f of 1r. But now remember that f of x was equal to y. So we get that that's in turn equal to y times f of 1r. So if you look at the beginning and end of that chain of equations, you get that y is equal to y times f of 1r. And you can make a similar computation where you have y equals f of 1r times y. So since y was arbitrary, we see that f of 1r is acting like an identity on S. And so that's our conclusion, that f of 1r is the identity in S. So there's a fairly important corollary of theorem 3.10 that involves the image of a ring homomorphism. And to fully understand that corollary, we first need to remember what's meant by the image of a function. So if you have a function, f from R to S, the image of that function is essentially the range, right? It's all the things in S that are hit by something back in R. That is, it's all the elements y in S such that y is equal to f of x for some x back in R. So this image is a subset of S, and if f is onto, then the image of f is the entirety of S. Okay, so now the corollary says that if f from R to S is a homomorphism, then that image set is actually a subring of S. So here we're going to prove that corollary. So remember that we had a theorem a little while back that said that if you want to show something as a subring, you need to only need to show that essentially that it's closed under multiplication and subtraction. So we pick two things in the image, R and S, and because those things are in the image of our function f, we know that there are elements a and b back in R where little r is equal to f of a and little s is equal to f of b. And now if we take r minus s, we can write that as f of a minus f of b, But then we saw earlier from theorem 3.10 that that's just equal to f of a minus b. So that means that r minus s is f of something, and therefore r minus s is again in the image of f. Similarly, r times f is f of a times f of b, but then remember that f is a homomorphism, and that means that that f of a times f of b is exactly the same as f of a times b. Therefore, r times s is f of something, and therefore r times s is again in the image of f. So that means r minus s and r times s are again elements of the image of f, and it's therefore because image of f is non-empty and closed under subtraction multiplication, we know that the image of f is a subring of s. Now you might be wondering how we know the image is non-empty. Well, remember that f takes, every ring has a 0 element, and f takes 0 to 0. So the 0 element in S is automatically in the image of f. Okay. So we finish today with a fairly interesting example, I think. So here we have, in items A through E, we have a pair of rings in each instance, and we want to establish that these rings are not isomorphic to one another. So the first pair of rings is the ring E of even integers and just the plain old ring Z of integers. So those two, they have the same cardinality, so there's a one-to-one and onto function from one to the other, but there is no isomorphism because the ring of integers has an identity, multiplicative identity, remember, but the even integers does not have any such thing. Moving on to item B, we have the Cartesian product 4 times of the real numbers, and then we have this set M super 2 by 2 of R, which consists of all the 2 by 2 matrices with real entries. And, well, why can't these be isomorphic? So the reason is that the first ring, the Cartesian product, that's a commutative ring, meaning it doesn't matter what order you multiply things in. But in the ring of matrices, we remember that that ring is not commutative. So those cannot be isomorphic to one another. Part C, we have Z4 cross Z14 and Z16. And if you look at it, the first ring, the cardinality of that ring is 56, I believe. There are 56 elements in that ring. And there are 16 elements in the second ring. So, you know, you don't even get off of, you don't even get to first base here, right? These two rings are of different cardinality. There's no way you can even get a bijection between them. So you have no hope of getting an isomorphism. Okay, part D, we have the ring of integers cross Z2 and the ring of integers. This one might cause us to think for a little bit. Remember that the second ring, the ring of integers, is an integral domain, meaning that there are no zero divisors in particular. But the first ring, you do have zero divisors, and you might want to take a moment now and just see if you can find a pair of zero divisors in Z cross Z2. Okay, finally in part E, we have the ring of rational numbers and the ring of real numbers. This is sort of an interesting example. One way that you could see that these two rings are not isomorphic is that they actually have different cardinality. Meaning, both of them are infinite sets, but they have different sizes. There is no one-to-one on and onto function from the ring of rational numbers to the ring of real numbers. That's something you might learn in an introductory analysis course, for instance. Now, let's suppose you didn't know that, which probably you didn't know that. There's still another way that you can show that there's no isomorphism from R to Q. So let's suppose that for a contradiction that we did have an isomorphism F from R to Q. Well, we know from theorem 3.10, from theorem 3.10 that F of 1 would have to be equal to 1, right? And then if you apply the additive property, say, of isomorphisms, that would tell us that F of 2 is F of 1 plus 1, which is F of 1 plus F of 1, which is 1 plus 1, which is again 2. So that tells us, using the multiplicative property of homomorphisms, that F of the root of 2 squared would have to be equal to 2. And so that means that F of the square root of 2 would have to be either plus or minus the root of 2. But the problem is that neither one of those numbers are rational. That's something that we have actually proved in the past in this course. And so there cannot be any isomorphism from R to Q.